If a web page takes 3 extra seconds to load, you might refresh the browser. But if a pacemaker or an anti-lock braking system takes 3 extra seconds to process a command, the physical hardware fails completely. In real-time software engineering, we operate under a strict rule. A correct calculation delivered past its deadline is a wrong answer. To prevent those timing failures, we rely on a software requirement specification, or SRS. For real-time systems, the most critical areas of this document are Section 4, which defines external interface requirements, and Section 5, covering other non-functional requirements. We can see how this works in practice by looking at the Safe Home Security System. This system must monitor physical sensors, process keypad inputs, and trigger a control panel without hesitation. If we document the requirements for Safe Home using the loose, descriptive language typical of a standard web application, we guarantee failure. We have to tighten our parameters. A real-time system is entirely reliant on its physical sensors. Because of this, the software needs to know exactly how data from a door sensor or a motion detector enters the system. This diagram shows the two main data retrieval methods. On the left is polling, where the software runs in a continuous loop, repeatedly asking the hardware if anything has changed. On the right is a hardware interrupt, where the sensor itself pushes a signal directly to the software the instant an event occurs. Section 4 of our SRS must specify the exact mechanism. For Safe Home, we translate a basic hardware requirement into a precise specification. The system will utilize a 64-bit Boolean event flag to handle the hardware interrupt. Without explicitly documenting this transfer method, developers might implement a polling loop that consumes too much processing power, creating data bottlenecks and causing the system to miss a critical break-in event. Once the data successfully enters the system, every critical function that follows must be quantitatively bounded in time within Section 5 of the SRS. Writing "sound the alarm when a breach is detected" is a useless engineering instruction. It leaves the acceptable processing time completely open to interpretation. Instead, we specify that the software must trigger the sound alarm subroutine within 500 milliseconds of receiving the sensor-triggered event. By applying a strict mathematical limit, we turn a vague suggestion into a testable engineering specification. When we move to the testing phase, we can measure exactly whether the software passes or fails. Consider a scenario where multiple inputs happen at once. The alarm is currently ringing. The homeowner is frantically typing their deactivation passcode into the keypad, and at that exact same millisecond, a secondary motion sensor is triggered. How would you write an SRS requirement to handle these two asynchronous events? Pause the video and determine how you would prioritize them. To prevent the system from locking the user out while it processes the new sensor data, the SRS must explicitly prioritize the interrupts. User keypad inputs must be placed at a higher priority tier than secondary sensor triggers. Written requirements can occasionally contradict each other in complex systems. To prove our logic holds up, we use behavioral models, specifically state diagrams. Looking at this diagram, we map the exact transition paths. We can visually verify that the pathway from the alarming state to the deactivated state takes precedence over processing another alarm event. The text in the SRS dictates what should happen, but these behavioral models prove logically that it can happen safely. Here is what a complete synthesized SRS entry looks like for the Safe Home alarm trigger. We can deconstruct this specification into 4 distinct real-time elements. First, the core function. Second, the hardware interface method. Third, the interrupt priority level. Fourth, the strict time-bound constraint. This text checklist summarizes the real-time rule of 3. Number 1, quantify exact timing constraints. Number 2, define polling versus hardware interrupts. And number 3, prioritize asynchronous events. Mastering these rules shifts your perspective, providing the control required to architect mission-critical reality.